Assalamu alaikum. Welcome to the new lecture. So, in this lecture, I'll be continuing with the last class that we actually did not finish. So, it was voltage regulation. We'll be continuing with the topic voltage regulation. So, as we have discussed about this, as we have calculated the difference between V1 and V2, I will again discuss this. So, this is the transformer equivalent circuit. Refer to this secondary side, and it is phasor diagram. For a well-designed transformer, the voltage drop in this resistance and in this reactance is very small, and because of this, the angle between V1, that is this angle delta, angle between V1 and V2 is very small. So, by taking this approximation, we may assume that this V1 may be coincident to this E, or A and E will be coincident, or we can say that this V1 may be equal to OE approximately. That is what I have written over here. But OE is actually the summation of different line segments. OE will be equal to OB plus BC plus CE. So that's what I have written over here. OE is equal to OB plus BC plus CE. Okay, this angle is theta, this angle, and this angle in this triangle is 90 degrees, and this angle will be 90 minus theta. So this angle will also be equal to 90 minus theta because they are vertically opposed angles. This angle will be equal to 90 degrees. That means this angle will also be equal to theta, but here it is written as phi. This will be phi. So this angle and this angle will be same. Now BC, you will see that it will be the cos component of this phasor, that is that is IR phasor. So this will be equal to IR into cos of phi. Similarly, this CE will be equal to this phasor, or this line segment. So this line segment is actually a sine component of this IX of this theta. That means this CE, which is equal to this length, that will be equal to IX sine of phi. So BC is equal to IR cos of phi, CE is equal to IX sine of phi. Also V1 is equal to OE, that we have already discussed. So V1 minus V2, that means V1 we have taken at OE minus V2 will be equal to this OB, that will be equal to this distance, that is BC plus CE, that BC is equal to IR cos of phi plus IX sine of phi. It has taken I as a comma, it will be equal to R cos of phi plus X sine of phi, and in this case phi will be lagging. So for leading case we'll just discuss that also. It will be equal to, only difference will be here we will be having minus IR cos of phi minus X sine of phi. In this case phi will be leading. Now we'll discuss this. This is the phasor diagram for the leading power factor. This is VR. Current is leading to this by angle theta. So this IR into R. IR means this current I. I have written this is this current. That is the receiving end current. I have here mentioned it as IR. That's why here also we have written as VR. So this will be actually this voltage, that is V2. VR will be V2. This V1 will be Vs. So this VR will be equal to V2. So the voltage drop I into R, that is IR into R in this case, will be added, which will be in phase with this IR, and then a voltage phasor, that will be IR into X, that will be perpendicular to this voltage phasor, that will be in this direction, and then the voltage, net voltage, that is V1, or here it is Vs unit, that will be this point has to be connected to the top of or tip of this phasor. So this will be equal to V1. So I have redrawn the same figure. This angle will be delta, that is this will be now V1, this will be this voltage phasor up to this P will be V2. This will be V1, this will be V2. So this will be delta. So when delta will be very small, and for a small delta, B will coincide with O, that means this AB will be approximately equal to AO. So taking these distances, this AO can be written as AP, that is this, plus PQ minus OQ. That's AP plus PQ minus OQ, isn't it? So since this angle is theta, this angle is 90 degree, this angle is 90 minus theta. Okay, now in this triangle, this is 90 minus theta, this is theta, this will be theta. Again, theta in earlier case we have defined it as phi. That's a perfect triangle. So this PQ will be nothing but its cos component, that is IR into R cos of theta. PQ will be this, and this uh, OQ, that will be equal to BR. This OQ will be equal to BR. It will be the sine component of this voltage phasor, that is IR into X. So this OQ will be equal to BR will be equal to IRX sine of theta. So this VS or this V1 will be equal to V2 plus IR cos of theta minus IR sine of theta. So the voltage regulation, that is V1 minus V2 divided by V2. So in this term I have written in this form. So I hope you will understood that this Vs will be this V1, VR will be equal to V2. So it will be equal to IR, that in this case it is only written as I. So you can also differentiate this, that is cos of theta, R cos of theta minus X sine of theta divided by V2 into 100. This will be for leading load. This is actually the derivation for the same. When the load is thrown off, this V2 naught will be equal to V1. I have already discussed that this should be equal to V2 naught minus V2 divided by V2. When the load is thrown off, because in this circuit you can see that when the load is thrown off, the no load voltage at this terminal will be same as that of V1. That is what this means. So the voltage drop V2 naught minus V2 will be equal to I R cos of phi plus minus sine of phi. This will be now in general plus for lagging, minus for leading power factor. Where I is the full load secondary current, V2 is the full load secondary voltage equal to the value of V2 rated. Thus, percentage voltage regulation will be equal to V2 naught minus V2 divided by V2, where V2 naught is V1 into 100. So when this is given to this, it will be equal to V1 minus V2 will be equal to this and this for different power factors. So it has combined both these in the single equation. So it will be equal to IR cos of phi plus minus X sine of phi divided by V2 into 100. So in per unit, as we know, this R base can be calculated by the voltage base divided by the current base, and voltage base is usually the rated voltage. So V2 is already rated, and this current base is also taken as the base current, full load current. This is the full load current. So V2 divided by I will be the R base or Z base. When you divide R divided by this R base or Z base, it becomes a per unit, R per unit, that is R per unit. Similarly for X, so this will be the Z base, that is V2 by I will be Z base. X divided by Z base will be equal to X per unit. So the per unit voltage regulation will be equal to R per unit cos of phi plus minus X per unit sine of phi. So from here on, for small delta, we'll be using this formula to calculate the voltage regulation. But V1 could also be calculated from the phasor equation. V1 is equal to V2 plus I angle of phi into R plus Jx. You can calculate it from here. You can see this is I, this is V2. Taking V2 as a reference, this V1 will be equal to V2 plus IR plus Ji into X. So in other words, we can say that V1 will be equal to V2 plus I angle of phi into R plus Jx. So in this equation, this will be the exact or accurate value of the V1 that will be calculated over here. But since this is an approximate value, you can calculate V1 by this OE, that is this OE will be equal to V2 plus this value. But in this case it will be very accurate and it will be very simple, because this equation involves the phasor sum or complex numbers. Here this does not involve that. Definitely there will be some error using this and this. This is the accurate one, this is the approximate one. There will be some error, but that error will be very small to be neglected. And here we are reaching to the final result much quicker, and it will be, as I have told you, error will be very small and we can consider it to be quite accurate. But this will give you the exact value of V1 as compared to this one. So that is why this equation is dependent upon the delta. If delta is very large, then you cannot use this equation, you have to go for this equation. Now let us calculate the maximum voltage regulation. What will be the maximum voltage regulation and what will be its relation with respect to the power factor? It is seen from the above equation, voltage regulation varies with the power factor and has a maximum value when we differentiate it with respect to theta, we can get, and equate to 0, we can get the maximum value. That means minus r sine of phi plus x cos of phi, when you differentiate this with respect to phi, that should be equal to 0. That means r sine of phi should be equal to r cos of phi. That means sine phi by cos phi should be equal to x by r. That is tan phi should be equal to x by r. In that case, this phi should be equal to phi z. You'll see if you draw the impedance triangle of the transformer, you will see on the real axis we have r, on the imaginary axis we have x, and their hypotenuse will be equal to z. And the base angle, that is the angle between hypotenuse and the r, will be the impedance angle theta phi z. So here this tan phi, that is the power factor angle, should be the tan inverse of x by r. That when you calculate from the this uh, impedance triangle, that will be equal to phi z. That means the angle between angle of the impedance of the transformer when it is equal to the power factor load, at that time voltage regulation will be maximum. Voltage regulation will be maximum. So calculating cos of phi, when you know the tan of phi, that means phi, in that case x will be perpendicular, r will be hypotenuse, sorry, base, and z will be hypotenuse, where z is equal to square root of r square plus z square. So cos of phi will be equal to r divided by, that is the power factor. Power factor of load should be given in terms of the parameters of the transformer. That will be r divided by r square plus x square lagging. Cos phi will be equal to r by z lagging. So it implies that the voltage regulation is maximum when the load power factor, that should be lagging, angle has the same value as that of the angle of equivalent impedance. That means phi should be equal to phi z. So one more thing that should be noted over here, that for lagging power factor, voltage regulation will always be positive, as well as for the unity power factor. That means for lagging as well as unity power factor, voltage regulation will always be positive. That means in this case, this V2 naught will always be greater than this V2 in case of lagging power factor and unity power factor. Now, from the above equation, the voltage regulation can be 0. That means when the voltage regulation can be 0, we can take that this equation minus equation. So in that case, r cos of phi minus x sine of phi. That means in leading case, r cos of phi is minus x sine of phi is equal to 0. That means in this case, when we calculate it as tan phi, it will be equal to r by x, the inverse of the earlier one, and it should be leading. That means phi will be now equal to 90 minus theta z. In this case, this power factor angle and the impedance angle, if they are complementary angles, volt and the power factor should be leading. In that case, cos of phi will be equal to x by z leading. It will be voltage regulation will be 0. But here you need to take you should be very careful that tan phi should be r by x, but in leading. If it is lagging, this does not hold true, because we cannot use this equation in that case. So first the power factor should be leading, and then tan phi, that is the power factor angle, should be equal to, or power factor of the load should be equal to x by z leading. So in this case it will be 0. If r cos of phi is less than x sine of phi, voltage regulation will be negative. For this case, if r cos of phi is greater than x sine of phi, voltage regulation will be positive. For the case of the leading power factor, you will see that the voltage regulation can have all the three possible values. That means when r cos of phi is greater than x sine of phi, voltage regulation will be positive. When r cos of phi is equal to x sine of phi, voltage regulation will be 0. When r cos of phi will be less than x sine of phi, voltage regulation will be negative. So for phi that is leading larger than the given above, that means when phi increases above this, then this will be less as compared to this. The voltage regulation is negative. Voltage regulation will be negative. That is, secondary full load voltage is more than the no load voltage. That means in that case, when we calculate it, that means this V1 voltage will be less than this V2 voltage. As you increase the load, voltage will go on increasing. Now this is the complete variation of the voltage regulation at different power factors. In this case, percentage regulation versus R is given to be 0.015 per unit and X is 0.05 per unit. You can see from power factor unity, up to power factor 0, angle is equal to 0 to 90 degrees. Lagging power factor, the variation will be like this, and it will be always positive. And this is when angle is 0, power factor is unity, there will be some voltage regulation and it will be positive. And when the power factor angle is negative, that is the leading power factor, from here to here, you can see from this point to this point, this voltage regulation is positive. At this point, voltage regulation is negative, sorry, 0, and from here voltage regulation will be negative. So you can see from here tan phi, when power factor is equal to R by X, that is this leading, R by X leading, that is 0.015, that is 1 by 3, that phi is 30. That means if cos of phi is 0.866 leading, in that case voltage regulation will be 0. That is why we have used this equation. So if tan phi, that is the power factor angle, is X by R, that is the inverse of this, that is 0.05 divided by 0.015, that is equal to 3. Phi will be equal to 60 degrees. Cos phi will be equal to if cos phi is equal to 0.5 lagging, this voltage regulation will be maximum. You have to take care of these leading and lagging. For example, if you take tan phi R by X is this, it will again be equal to this. But if you say that this is lagging, you cannot say, in that case it will not be equal to 0. Voltage regulation will not be equal to 0. Voltage regulation will be 0 when power factor for this R and X is equal to 0.86 leading, and voltage regulation will be maximum when power factor is 0.5 lagging. It is, if it is 0.5 leading, it will not be maximum, it will be having some negative value and it will violate this equation. So you need to be very careful about leading and lagging. So condition for negative maximum voltage regulation, this occurs only when the power factor is leading and when phi is equal to 90 degrees. That means when the load is purely capacitive. In that case, V1 minus V2 is equal to I or cos of phi minus X sin of phi. So there will be V2. So when phi is 90 degrees, this will be 0. This will be equal to minus X. So it will be equal to minus I divided by V2 into X. This will be equal to minus X per unit. This will be the maximum value of the power factor. Sorry, voltage regulation in negative direction. So just to summarize all these things, if voltage regulation is 0, that means this theta or phi and phi z are complementary angles, or we can say phi z plus phi plus phi z will be equal to 90 degree, and in terms of R and X it will be equal to tan inverse of R by X. Power factor will be leading. For maximum, both the angles will be same, that is the power factor angle and the impedance angle will be same, and it will be equal to tan inverse of X by R. Power factor will be lagging. So voltage regulation will be negative when tan of phi will be greater than R by X. So, or we can say this X sin of phi, you can see when you take it over here, it will be sin of phi divided by cos of phi. X sin of phi is greater than R cos of phi. So it will be negative maximum when theta is 90 degrees. In that case, it will be equal to minus I into X divided by V2. VR is here equal to V2, to be equal to minus X per unit. In both the cases, voltage regulation will be leading, power factor will be leading. So 0 and maximum voltage regulation may be coincident when theta is equal to pi by 4. You can see when theta is equal to pi by 4, when theta this is pi by 4, this will be also equal to pi by 4. Here also this is pi by 4, this will be pi by 4. But for 0 power factor, 0 voltage regulation, power factor is leading and it is lagging for the maximum voltage. That is to be very much for that case you have to be very much careful. Now let us try to do some numericals. So you will get quite acquainted and it will be quite easy for you to understand this type of concept. The following data were obtained on a 20 kV 50 Hz 2000 by 200 distribution transformer. Draw the approximate equivalent circuit of the transformer F4 to high voltage. This actually we have already drawn. Actually we need to take the data of this and use here to calculate different voltage regulations. With the full load on the low voltage side at rated voltage, calculate the excitation voltage on the high voltage side, the load power factor. If the load power factor is 0.8 lagging, 0.8 leading, what is the voltage regulation of the transformer in each case? First we have to calculate the voltage at the high voltage side and then the voltage regulation at this power factor and this power factor. The transformer supplies a full load current at 0.8 lagging power factor with 2000 voltage and 2000 volts on high voltage side. Find the voltage at the load terminals and the operating efficiency. So we'll try to do this, and we'll use actually this circuit which we have derived from the open circuit test and short circuit. Here we need not to calculate them again. We have already calculated it as circuit. This is the circuit which we have already calculated. So the high voltage equivalent circuit is shown here. So VL, first we'll calculate the load voltage on low voltage side and load current on the low voltage side. So this is given as 200 and load current will be equal to 20. It's not 200, it's 20 kV. You can see it is given as 20 kV. So it will be 100 amperes. 20 into 1000 divided by 200 will be 100 amperes. So VL dash, that is the high voltage side. Since we have to refer it to high voltage side, VL dash will be equal to 2000. IL dash will be equal to 10 amperes. That is on the high voltage side. So we are referring it to the high voltage side. So VH, that means this side voltage, will be equal to this voltage plus this voltage drop. So this voltage drop will be actually taken from the earlier one, which we have already calculated. So it will be equal to VL dash plus IL dash into RH cos of theta plus minus XH sine of theta. So we have to use here in first case plus for lagging power factor. In second case we have to use minus for leading power factor. Given that cos phi is equal to 0.8 lagging and sine phi will be equal to 0.6. You can calculate cos inverse of 0.8 will be phi, and then you can calculate the sine of phi, that will be come out to be 0.6. And you should remember this combination: when cos phi is equal to 0.8, sine phi is equal to 0.6. So VH is equal to 2000 plus 10. This is 2000. This is 10. RH is 10. 3. You can use this is 3. This cos of theta is 0.8 plus 5.2 is this value, and 0.6 is this value. It comes out to be 2055.2. So the voltage regulation for this case will be equal to this is VH. We have calculated already the value of the high voltage side excitation voltage. First, what is the voltage? Now, calculated excitation voltage on high voltage. We have calculated this. This is equal to 2055.2. Now voltage regulation will be this voltage minus this, that is V2 no load. That means no load. When there is no load, this voltage will be same as this voltage, that is 2055.2 minus 2000. That's the full load voltage minus full load voltage. That is full load voltage. It comes out to be 2.76. Now for the second case, the power factor is 0.8 leading. Sine phi will be again 0.6 leading. So VH is equal to same equation, but here we have to use the minus. That's 2000 plus 10 into 3 plus 0.8 minus 5.2 into 0.6. It comes out 1992.8 volts. So when you calculate this voltage regulation, because this is the high voltage side voltage, and no load, this voltage will be same as this voltage. So no load voltage, full load voltage, or full load voltage comes out to be minus 0.36%. So in that case, in this case, you'll see that the voltage regulation is negative. No load voltage is less than the full load voltage. Now the B part is the transformer supplies full load current at 0.8 lagging power factor with 2000 voltage on 2000 volts on high voltage side. We are supplying the high voltage side with 2000 volt. We need to find out the voltage at the low terminal. Low terminal voltage we have to calculate, and operating efficiency. So this VL dash will be equal to this VH minus this voltage drop. So approximately we can use the same formula, that is VH minus IL into RH cos of phi plus XH sine of phi. Power factor is given as lagging, so we have to use here plus. So 2000 minus 10 into 3 into 0.8 plus 5.2 into 0.6, that is equal to 1944.8 volt, and that is this voltage. VL dash will be this, or VL will be this. So what is actually the question? Find the voltage at the low terminals and operating efficiency. We need to find out this low terminals, and since load is calculated to the low voltage side, so that's why we have calculated this low voltage voltage at the low voltage side. So efficiency will be equal to P naught VL IL cos of phi. VL is this, IL will be 100, full load cos of 0.8 is 155.8.4. So core loss will be equal to Pi plus Pc. We have already calculated, it is given here in the question itself. Core loss is given 120, copper loss is 300. So it is given to be like this. So total loss will be 420. So efficiency will be equal to 1 minus 420 divided by this. Actually this should have been here plus 420 divided by input plus this, it will be equal to 97.38. We can use that also, that is output, that is 15558.4 divided by 1.58.4 plus 420, it will be all same. Now let us try to do one more numerical. For a 150 kV 2400 by 240 transformer whose circuit parameters are given in the example 3.8, that is this circuit parameters are given like this. Draw the circuit model as seen from the high voltage side. Determine therefrom the voltage regulation and efficiency when the transformer is supplying the full load at lagging power factor on the secondary side at rated voltage. Under these conditions, also calculate the high voltage side current and its power factor. So the circuit parameters are like this. So this is 10 kV, this is 10 kilo ohm, this is 1.6 kilo ohm, that is this. So we'll refer it to the high voltage side. So this will be equal to 0.2 plus its transformer ratio is 10. So our high voltage will be equal to 0.2 plus 2 into 10 upon minus 3 into 100, that's n square. It is 0.4. So x high voltage will be equal to 0.45 plus 4.5 into 10 upon 3 into 100, that is 0.9. 0.9, this plus this, so this will be like this. So this is the sequence circuit. The first one was this. Draw the circuit model as seen from the high voltage side. We have draw the circuit parameters seen from the high voltage side. Determine therefore the voltage regulation. So to calculate the voltage regulation at full load 0.5 lagging, so we need to first calculate the high voltage side full load current. That would be 150 into 1000 divided by 240. That is the low voltage current, or you can calculate the current on the high voltage side. You have to divide it by 2400 or divide it by 10 to be 62.5 amperes, 0.8 power factor lagging on low voltage side. On high voltage side. So V2 will be now, V2 dash will be 2400, but V2 will be 240, I2 will be 62.5 amperes. So V2 dash will be 2400, V2 dash will be 2400. So voltage drop in this will be equal to 62.5 into 0.4 into 0.8 plus 0.9 into this will be voltage drop. It will be 53.75, or you can directly calculate from this to this, that V1 is equal to 2400 plus this value. So it comes out to be 2454 approximately volts. Voltage regulation will be equal to 53 or this 2454 minus 2400 divided by 2400 into 100, it will be 2.24%. Now output power will be equal to 150 into 0.8, that is full load, and full load voltage is 120 kilowatt, this is power factor, and 150 is kVA. Copper loss will be in this winding, so that will be equal to 62.5 square into 4, that is 1.56 kilowatt. Core loss will be the loss that occurs in this, that is this voltage square divided by this resistance, that is 2454 square divided by 10 into 10 divided by 10 kilo ohm, that is 10 into 1000, that is 0.6 kilowatt. So total loss will be equal to 2.16 kilowatt. So efficiency will be equal to 120 divided by 120 plus 2.16, that's 98.2%. So this I naught will be equal to this V1, that is this voltage divided by 10 kilo ohm plus J timers plus this V divided by J into 1.6 kilo ohm will be I naught, that is this. So when J is taken outside, take to the numerator, it will be minus, so this will be the value of I naught. So I2 dash will be equal to 62.5 at an angle of this minus 36.86, that's the cos inverse of 0.8, or you can say its real part is 0.8 and imaginary part is minus 0.6. So when you multiply it by the 62.5 on high voltage side, this will be I2 dash. So I1 will be equal to I naught plus I2 dash. So you have to add this current to this current, it will be finally 63.63 at this. So I naught will be equal to 63.63 at an angle of this, and it will be equal to 0.79 lagging. So this is about the voltage regulation. I hope you have understood this. Now let us move to the next topic, that is the auto transformers. So what is this auto transformer? An auto transformer is a transformer in which a part of the winding is common to both the primary and secondary circuit. That type of transformer is known as auto transformer. We'll see this. In a two-winding transformer, primary and secondary windings are electrically isolated, but in an auto transformer, the two windings are not electrically isolated, rather a section of the same winding acts as a secondary or primary of the transformer. So you can see over here we have, and this auto transformer is known as is actually known as the single winding transformer. You can see we have a single winding over here. So in between A and B, it's a single winding. We are giving the input, and in between B and C, we are taking the output. So this is actually, this B and C is common between input and output. So you can see that this is a auto transformer. Also, you can see there is a direct connection between the input and output through this A and C. So there is no electrical isolation. So what is the construction? The core of an auto transformer may be rectangular or circular type in shape. The core may be of this type, or it may be of this type, circular shape or rectangle. A single winding is wound around one or two limbs of the rectangular core, or it will be around the ring. So we may have a single winding around wound around on this limb or this limb also, depending on what is our requirement. Terminal B is taken as a common point from which one terminal for the primary and one terminal of the secondary is taken out. You can see terminal B over here or terminal B at here. It is common between input and output. Terminal B is common between input and output. Terminal B is common between input and output in every case. You can see over here. Here also this terminal B is taken as common between input and output. That means this B terminal will be one of the terminals of input as well as output. The second terminal of the secondary is connected to the point C, which may be fixed or movable as shown in 1B and 2B. You can see second terminal is connected at the output at point C. So it may be fixed over here, or it may be movable upwards, downwards, so that output voltage may vary. So terminal C, or we can say the output is connected between B and C, and this C may be varying or movable in circular motion or in the translation motion. So when this moves in this direction, voltage will decrease, and when this moves in this direction, voltage will increase. So when this moves upwards, voltage increase. When it moves downwards, voltage will decrease. The number of turns between A and B are taken as N1. That means the number of turns between A and B are taken as N1, and number of turns between B and C are taken as N2. So the number of turns N1 and N2, that's one section of the same winding acts as primary, and the other section of the same winding acts as second. When the number of secondary turns N2 is less than the primary, that is this, if N2 is less than primary, it's a step down transformer. So this is also a step down transformer. You can see here point C and B has less number of turns as compared to point A and B. This is a step down transformer. Or if the number of N2 turns are greater than N1 turns, it acts as a step up transformer. For example, here N2 is greater than N1, it's a step up transformer. Here you can see the number of turns between C and B is greater than between A and B, it will be a step up transformer. Here also, if we connect this point C to C, it will be a step up transformer, and if we connect this C to, we can see 4, 3, 2, 1, it will be a step down transformer. So I think I will stop over here. It is enough for today. We will continue in the next class. Thank you.